So, thank you, Mr. Chairman. Thank you, everyone, for attending my presentation. And yeah, maybe we are a bit late. I will try to be fast, but the ability to synthesize is not my best here. So, my presentation today is about fatigue propagation in shell member alloys, and in particular, I will show some preliminary results related to a novel energetic approach. I don't know, is something wrong? Okay. In particular, we analyzed the binary nickel titanium system. That is a unique class of material that show extraordinary high force and shape recovery capabilities through the so-called shape memory effect and pseudoelastic effect or superelastic effect. Both these properties are due to a fully reversible solid-state transition between two distinct crystal structures, austenite and martensite, that can be activated either by temperature and or by applied stresses. However, it is well known that these shape memory alloys exhibit a very complex constitutive behavior with nonlinear hysteresis and intricate thermomechanical coupling mechanisms. And in addition, it is widely accepted by the scientific community that this transformation occurs locally, and these local effects play a very important and dominant role on material damage, especially under fatigue loading conditions. That's why we started studying fatigue and fracture of shell memory alloys a few years ago, because they exhibit a completely different behavior with respect to common engineering metals. In particular, we focus on macro crack, I mean, the one in which the size is much larger than the typical microstructural details, I mean, the grain sites. And yeah, unfortunately, in that case, solid mechanics theory can be used, but unfortunately, standard theories and approach cannot be directly applied to shell memory alloys due to these complex phase transition phenomena and local effects. That's why spatial methods must be used, sometimes involving multi-scale simulation ranging from atomic to component scale. Now let me start with the core of my presentation. I will try to give a very quick overview about research activities we did in last year, and with a focus on the experimental methods and models we have developed, and finally the results on fatigue growth with the focus with the preliminary results on the novel energetic approach we are developing. So a few information about local phase transformation. The high stress gradient, the strain gradient near the crack tip pose marked stress-induced transformation. And this stress-induced transformation have a very important effect on the wall stress strain distribution near the crack tip that have a significant effect on both fracture and fatigue properties of shell memory alloys. So these, unfortunately, these local effects are also observed under nominal uniform stress conditions as shown here. And this causes also a very unusual fatigue response of shell memory alloys. So to this aim, we developed the spatial experimental methods. We are using high resolution digital image correlation to capture these local effects. And we are also using infrared thermography to capture the thermal effect associated, linked to latent heat of transformations. And we are also using instrumented run indentation to capture localized transformation. About modeling, we have developed a simple model that is based on a modified version of the Irwin's correction to linear elastic fracture mechanics. It is based on the definition of an effective crack length stress intensity factor that is able to take into account the large process stress-induced zone near the crack tip. And the method is able to predict both the extent of the stress-induced transformation region, but also the wall stress strain distribution near the crack tip. So we developed also a nonlinear regression method that uses the displacement data captured by high resolution DIC to obtain effective crack length stress intensity factor by the Williams expansion series. And finally, the non-indentation. We developed spatial methods and parameters to predict to capture local transformation from the nano indentation cubes of the material. So let me move the results. We analyzed two different types of the two microstructure, basically austenite and martensite. We use a single edge crack sample obtained from commercial nickel titanium materials. And we have also tried to analyze to capture the effects of temperature, to capture the effect of thermomechanical coupling, because there is, when increasing the temperature in a pseudoelastic material, the stress plateau increases significantly with a ratio of about 10 megapascal per Celsius degree. And okay, this is an example of the results we obtained from the high resolution DAC and indentation. So we are able to capture the strain field in the near crack tip region and consequently the transformation zone. And we have observed the marked effect of the temperature on the phatic crack propagation cubes. Here you see the evolution of crack length versus the number of cycles. For the same material at different temperature, 25 to 65 degrees, there is a marked effect of the temperature, and also a comparison between the two microstructures. You can see the martensite has exhibited a much longer phatic life. We built the crack propagation cubes as a function of the effective stress intensity factor captured by our special methods. And we have observed that there is a marked effects of the temperature in pseudoelastic, but also a marked effects of the microstructure. That's why now we are looking at a different parameter. So we are trying to understand if these effects are obviously related to the material hysteresis. So in the case of austenitic material, they exhibit a fully recovered pseudoelastic response with the marked temperature effect. I mean, the stress increases with increasing the temperature. And in the case of martensite, the martensite is a pseudoplastic material. The deformations are reversible. They can be recovered by heating. So that's why we are trying to use the so-called the dissipated energy. So that is the energy within the stress strain transformation cube of the material. And this parameter can be calculated by basically two methods. A so-called global method that is from the force displacement cube obtained from the testing machine or by numerical simulation. Or the other method is a local approach that is a volume integration in the near crack tip region as obtained from FEM simulation. To this aim, we performed complex FE simulation by using ad hoc and fully coupled thermomechanical model for Hashemi memory alloys. And we did this energy calculation. We compared the two results, the two methods. They are in good agreement. And now we are trying to analyze phatic crack propagation data as a function of these energetic parameters. And from the first result, it seems that they fit perfectly the experimental data. I mean, this parameter is able to take into account the effects of temperature and the effects of microstructure. And finally, conclusion, I don't know if I have more time. So we have shown that we have observed localized transformation by different techniques. This transformation, near crack tip transformation, are significantly affected by temperature and microstructure, and they play a very important role on phatic crack propagation. And this parameter, this dissipated energy, seems to be a very good parameter to analyze, to take into account these local transformations. And as a future works, we are going to do experiment to analyze the effects of loading ratio, loading frequency, crack closure, and so on. Thank you. Can you make a paper?